Hello guys, welcome back to my channel once again. I hope you are doing absolutely fine. Today we will start power MOSFET. We have previously seen power BJT and now we are starting power MOSFET. Now the MOSFET stands for metal oxide semiconductor field effect transistor. We will explain each and every part in detail. So let us start. Let's see what are the key features of a power MOSFET. First of all, high input impedance. Okay. The first key feature of a power MOSFET is its high input impedance. Second, high switching frequency. High switching frequency. The power MOSFET switching frequency is more than power BJT. It is generally used greater than 200 kilohertz. In this frequency range, it is generally used. Next, it is unipolar device. It is unipolar device. Okay. It means it can withstand voltage in a particular direction. Either forward voltage or reverse voltage, but not both. That's why this is unipolar. Next is that a power MOSFET or a MOSFET has a input capacitance. So we will also see that how a power MOSFET possesses input capacitance property. We will see that. Okay. Its conduction loss is more. In BJT, the switching loss is more, but in power MOSFET, the conduction loss is more. That's why we can use power MOSFET in high frequency region. And there is no secondary breakdown. Like BJT, one major problem of power BJT is that it suffers from secondary breakdown. But power MOSFET has, the manufacturer or the engineers has eliminated the secondary breakdown problem in power MOSFET. So no secondary breakdown. Okay. So these are the key features of a power MOSFET. Its high input impedance. Next, high switching frequency. Next, it is a unipolar device. Next, it has an input capacitance. Next, its conduction loss is more. Next, it do not suffers from secondary breakdown. So, let us see the basic structure, the design structure of a power MOSFET. First, let me draw a normal low power MOSFET. Then we will see what are the modifications that have been done for a power MOSFET. See, this is the basic structure of a MOSFET. It has again 3 terminals. Like your BJT, it has again 3 terminals. The base of the BJT resembles the gate of the power MOSFET, the gate terminal. So, gate. Next is your drain. Drain resembles the same characteristic as your collector terminal. So, again, drain. And the source terminal, it is similar to the collector terminal in a power BJT or in a normal BJT. So it has 3 terminal: gate, drain and source. And one thing you notice, they are similar in their working nature like in BJT. So source acts as a collector, drain act as a source act as a emitter, drain act as a collector and gate act as a base. So this is base in BJT, this is drain means collector in BJT. The working principles are same. The characteristics are also same. Source is like your emitter. Okay. Now, see, this is a P substrate and two N plus layers are doped in the P substrate. See, this is the source terminal, this is the drain terminal, and this is gate. And this is insulated by a oxide called SiO2, silicon dioxide. Okay, SiO2 layer. Now, this is also act as an insulating material. See, what is the working principle now? Whenever the gate terminal is not being applied any voltage, there is no current flow. But whenever you apply some voltage in the gate terminal, that means the voltage must be negative at the source terminal and positive at the gate terminal. That means there is an electric field that is established in this layer. Is like this. An electric field has been established like this. Now what happens? In P substrate, holes are the majority carrier. So holes move away because of the repulsion of this positive ions. What happens? The electrons get accumulated here. So there is a channel formed. There is a channel of electrons which is formed in between two N plus layers. So what happens? A current flow like this. Okay, this is the direction of the current flow. So what is the working principle? First, when you apply some gate voltage, which is negative with respect to source, there is an electric field which is established in the insulating material. Then what happens? Because there is a positive ions are here, so in the P substrate, what you have, P substrate, you have holes as majority carrier. So the holes get repelled and they get downwards, and the electrons, they get accumulated here. What happens? The channel is formed, and that's why this is known as it is an electron channel. This is known as N channel MOSFET. N channel. Okay. And one thing you notice, if you apply more voltage at the gate terminal, which is, what is that voltage? VGS. Okay, this resembles gate, this resembles drain, and this resembles source. So when you apply VGS, that means gate to source voltage, and if you increase the gate to source voltage, what will happen? There the channel width will be more. So that's why sometimes they call it N channel enhancement type power MOSFET. N channel enhancement type. Why they are calling enhancement type? Because if you increase the gate to source voltage, what will happen? The channel width will increase, and that's why channel width is enhanced. That's why they call it enhancement type MOSFET. Now let me summarize what is the working principle. You are applying the source voltage, gate to source voltage, you are applying some voltage, then an electric field is established. That's why, as the electric field is established, that's why this is called the field effect transistor. Okay, as the current flow is due to this electric field. Why the current flow is due to this electric field? This electric field enables the channel growth. That's why this is called field effect transistor. And why metal oxide? Because a metal oxide is used for the insulating material, which is silicon dioxide. So an electric field is induced, and then the P substrate, you have positive holes which serves as a majority carrier, and as the positive majority carrier is repelled from these positive ions which is there in the electric field, so the electrons move up and they form a channel, and that's how a current flow from drain to source. Similarly, in BJT, what we have seen, there is a current flow from collector to emitter, but the electron flow is from emitter to collector. Similarly, in your power MOSFET, the current flow is from drain to source, but the electron flow is from source to drain. So, what are the things that we have learned? Why this is called N channel? Because this is the negative electron channel which is formed. Why it is called enhancement type? Because if you increase VGS, if you increase get to source voltage, then what happens? The width of the N channel, width of the channel increases, and as the width of the channel increases, so that's why it is called enhanced. The channel is enhanced. So metal oxide semiconductor field effect. Why this is field effect? Because of this electric field. This is an electric field. Because of this electric field, you have the current flow. Okay, and remember one thing, MOSFET is a majority carrier device. It is a majority carrier device. We will see which enables the higher frequency operating range. So, this is the basic structure of a low power MOSFET. But what happens, the on-state resistance of this low power MOSFET is very, very high. So we design a new kind of MOSFET which is called VDMOS, vertically deflected metal oxide field effect transistor. We will see now. So see here, I have drawn this figure of power MOSFET. Now see what are the changes here. The source is divided into two parts. First of all, the source was only one terminal. The source is divided into two parts, and you have a N plus layer over here, and this is a P substrate. This is the P substrate, and this N minus layer is induced here for the what? In power diode we have seen N minus layer withstands the more voltage. So the voltage withstanding capability is increased here as it is a power MOSFET. The name of this MOSFET first of all is VDMOS, that is vertically diffused metal oxide field effect transistor. Okay. See, the source terminal is divided into two parts, and the drain is shifted over here. The drain terminal is shifted over here, and the gate is as it is. Now initially, if you don't apply any VGS, that means get to source voltage, with respect to source keeping the negative part, see, source keeping the negative part, there is no operation in the MOSFET. Now what happens if you apply some VGS? So if you apply some VGS, again an electric field is produced in the insulating layer. This is the insulating layer SiO2. This is the insulating layer SiO2, and you can see these are the metallic terminals which is there. This is also metallic terminal. Now what happens, as the electric field is generated, again this is a P substrate. So what happens here, again a channel is formed, because again we know as P substrate contain majority carriers as holes, so the holes move away, holes is repelled by these positive ions, and the electrons get accumulated over here. Again the electrons get accumulated over here. Okay, the electrons get accumulated. Now what happens? This is N plus, that is, it is having more electrons. It is also N plus, it is having more electrons, and now a channel is formed. Now there is a current flow like this. The current flow is like this. It is again from drain to source. The channel is formed. Again you can see this is the direction of the current flow. Again you can see as you increase this voltage, the electric field gets stronger, and this channel width is again gets increased or enhanced. That's why it is again called enhancement type N channel power MOSFET. Suppose we are using P substrate over here and N substrate over here, then that MOSFET will be called P channel enhancement type. Then there will be some positive ions which will be accumulated over here. Okay. Now I have explained. Next, you can see if you increase VGS, okay, if you increase VGS, your current flow, your channel width is increased and your current flow is established only when you apply VGS. That's why MOSFET is known as voltage control device. It is a voltage control device. But on the other hand, in BJT, you have seen that if you increase the base current, then only the device is triggered or it is turned on. So the power BJT is a current control device and power MOSFET is a voltage control device. Next, we were talking about the input capacitance. Now let us see how the input capacitance is formed. This is a metallic layer at the gate. This is a metallic layer and gate is the input terminal, very similar to the base. As base was the input terminal of BJT, the gate is the input terminal of your MOSFET. Now see, this is a metallic terminal and again you have a N. So this is negative, this is negative. And see, this is not only negative, this is also a conducting part. So this is a conducting part and this is a conducting part, and you have an insulating layer of SiO2. Now any two conducting plates separated by an insulating layer will be called a capacitance. That's why we may call that the MOSFET has an input capacitance because of this insulating layer. See, this is a conducting terminal, this is also a conducting plate. You can say terminal or plate, and it is separated by a insulating layer. This is SiO2 layer. That's why MOSFET is called having a input capacitance. That's why it is called to have a input capacitance. Okay. Now let us see what is the basic symbol of a MOSFET. Let us see. Okay, before going to the symbol, let me tell you one thing. In power MOSFET, we have some parasitic BJT. Let us see how that is formed. See, this is a NPN. So NPN means a NPN transistor. So there is a parasitic transistor which is formed. Now, what is the emitter? See, this is the emitter. This is the emitter. Why this is the emitter? Because N plus region has more doping of electrons. That's why this is emitter. And this P act as base and this is collector. So this is a parasitic BJT that is formed in a MOSFET. Again we can see there is a parasitic diode also. PN. So there is a diode. So PN, there is also a parasitic diode, or it may be called an anti-parallel diode or body diode. That's why you can see in some of the MOSFET symbols there is a anti-parallel diode like here, like this. So why that anti-parallel diode? See, PN, so this forms a diode. So this is a anti-parallel diode or body diode. Sometimes it is called a body diode. A body diode or a anti-parallel diode. And see, for this BJT, how this BJT is non-functional. See, its source, it is the emitter and the collector both are shorted by the source terminals. See, both are shorted by the source terminal. That's why the effect of the parasitic BJT is not pronounced. The effect of parasitic BJT is not pronounced, but the effect of body diode is pronounced. That's why you can see in your MATLAB simulation also, you can see in MATLAB there is a default body diode with a MOSFET. That's why a PN connection. That's why that is a default body diode. And one thing you remember, the effect, how the effect is nullified, as the source short, this is your emitter terminal of the BJT and this is your collector terminal. Both collector and emitter are shorted by the source terminals of the BJT. See, the emitter is connected in the source and emitter is also connected in the source, like this. Okay, So that's why your effect of parasitic BJT is not there, but the effect of your parasitic body diode or antiparallel diode is there. So what are the characteristics? An antiparallel diode, an input capacitance is there in a power MOSFET. See this concept also. See why I am going at the back of the camera on and on, because I need to check that everything is coming inside the camera. This part was not coming. So this is body diode. Okay, this is your body diode or antiparallel diode, and this is your input capacitance. This your input capacitance. So this is your, let me write here, input capacitance. Now we will see the symbol of a BJT, symbol of a power MOSFET, and the other things. See the symbol of power MOSFET. So the symbol is this is your gate terminal, and this arrow represents the electron direction, not the current. Okay, this arrow represents the electron direction, not the current. So this is a N channel, this is gate. Okay, this is again drain, sorry, this is source, and this is your drain. This is gate, source, and drain. This direction of arrow represents your direction of electron, not the direction of current. In BJT we have seen the direction of arrow represents the direction of current, but not here. See, this is a N channel. Arrow going inwards means N channel. So arrow going outwards is your P channel. Okay. This is drain, this is source, and this is gate. This is your P channel. The symbols are remaining same for your power MOSFET and your also low power MOSFET. So why we have gone? So see, till now what we have studied, we have seen the basic low power MOSFET. What was the problem? The on resistance was withstanding capability of the first figure that I have done. The low power MOSFET is not that high. So what we have do, we have introduced another layer, N minus layer, for the more voltage withstanding capability. And we have seen how the input capacitance is formed, how your anti-parallel diode is formed, how your BJT is formed but that is shorted, the BJT is non-functional there, and how your input capacitance is formed. Now let us see some characteristics of the power MOSFET. See guys, now we will see some characteristics of the power MOSFET. So, characteristics. So before drawing the characteristics, let us draw a simple circuit like your BJT, like we have seen the common emitter mode. Now we see common source circuit. This is given VDD. Okay. This is your source. This is your VGS plus minus get to source voltage. This is your VDD. This is RD, and this is your direction of ID. This is coming, and this is your source current IS. Okay. So see, similarly for a MOSFET, we have drawn a common source. The source is grounded, and see this VDD represents the the VCC, collector to collector voltage in the case of BJT, and this VGS is the base to emitter or the VBE voltage. Now let us see. The first characteristics is being your transfer characteristics. Similar to input characteristics, the transfer. Okay. I think it is visible. Yes, it is visible. The transfer characteristics. Okay. The first characteristics being transfer characteristics. The transfer characteristics is between the ID, the drain current, and your VGS. Okay. And the curve is like exponentially rising, and this is your VGST. That means get to source threshold voltage. After some threshold voltage that you apply, then the drain current starts flowing. Other than the drain current is not exist here, does not exist. So this is the transfer characteristics, and this VGST, see this characteristics is same as your input characteristics of the power BJT, and this GST is about 2 volt to 3 volt range, not more than this, 2 volt to 3 volt range. Now let us see another characteristics, which is your output characteristics. See, there is not much space here, so I need to erase the diagram. So output characteristics. In output characteristics, the curve between your, see this is your drain to source voltage, na? VDS. In BJT, we have already seen this was emitter to collector to emitter voltage VCE. We have seen a curve of collector current to VCE, that is output. Similarly here, it is drain current to your VDS. VDS. The curve resembles same as your transistor curve, like this. Okay, and these are different VGS. This is of different VGS. So that is VGS1, VGS2, VGS3, like this. So if you increase the gate to source voltage, the curve will increase like this. And in this region, the transistor was operating in short switch, like the transistor was shorted. So that region was known as saturation. Saturation was divided into two, quasi-saturation, hard saturation. Here it is called ohmic region. In here also the MOSFET acts as a short switch, but the problem is that as the MOSFET is of high resistance, so this region is called ohmic region, and this is called active region. This region is called active region, and this lower region, when the MOSFET is off, it is called cut-off region. Cut-off region. So the characteristics remains the same. Again, if you obtain the expression of the drain current for load line concept, we have already done the load line concept in case of BJT. We have seen that we have drawn the we have calculated the collector current, then we have drawn the curve. Similarly, for this, the drain current is VDD minus VDS divided by your drain resistance RD. And if you see ID VDS, similar to your collector current expression in BJT, VDD by RD minus VDS by RD. So this represents the load line. What is load line? Load line we have already studied. It is the locus of all operating points. So this intercept is your VDD by RD, similar to your power BJT, this intercept was VCC by RC, and again the slope of this line is -1 by RD. This slope RD is drain terminal resistance. Okay, so this is the output characteristics of your power MOSFET. We have also studied the transfer characteristics, or you can say the input characteristics of the power MOSFET. So let us move on to the next topic. See, I have drawn the waveforms to save your time. See, when you apply some gate voltage over here, what happens? The gate to source voltage does not change instantaneously. Why? Because of the input capacitance. See, this is not changing instantaneously. It is taking some time. As we know, the property of a capacitance is to oppose the sudden change in voltage. That's why the voltage of VGS, the gate to source voltage, is not changing suddenly. It is taking some time. This change is change delay of the gate to source voltage is because of the input capacitance effect. How the input capacitance effect, we have already explained. So the input capacitance effect is not allowing the VGS to rise up sharp like your VG. This is your applied input voltage. Okay, and see, this is your VGST. That means threshold voltage. After some threshold voltage, the drain current start rising. Okay, again, suppose the device is now on. The device is on. Now what happens? See, after the immediate removal of your gate voltage, the device current, the device voltage, the VGS voltage is not rising sharply. It is again taking some time because of the, again, this is of the input capacitance effect. Input capacitance effect. And see, after the VGST, see, this is again VGST, the threshold voltage. After this threshold voltage, again the current is 0 and the device is off. So this period is turn on time, and this is your turn off time. So this is the switching characteristics. Let me explain again. If we apply some gate voltage, the gate to source voltage does not rise instantaneously because of the input capacitance effect. As we know, the capacitance opposes the sudden change in voltage. So it rises it takes some time to rise. Then after crossing the threshold voltage, this is the threshold voltage. This is also known as the threshold voltage. After the threshold voltage, the voltage rises to a certain extent, and then your drain current starts increasing, and it is increased. Now as it is increased, suppose you remove your gate voltage, then what happens? The gate to source voltage again takes some time to get 0 because of your input capacitance effect, and that's why it takes some time. And again, see, whenever it is the gate to source voltage reach to the threshold value, the drain current is 0, and you can see after that is 0. So this is the switching characteristics of the power MOSFET. Now let me explain why the power MOSFET is called it is used to have high switching frequency, because you know that first of all, let me erase this. I think you have understood this waveform. This is with respect to time waveforms. Okay, this is with respect to time. Now see, first of all, why high frequency application? High frequency application. The first reason is that first of all, it is a majority carrier device. It is a majority carrier device. So being a majority carrier device, the recombination of the other carrier is very, very little. That's why the turn off process is faster. So the turn off process of the MOSFET, the turn off time is actually less than or equals to 100 nanosecond, which is very small. That's why the switching loss is also small. Switching loss is small. So the MOSFET is used for high frequency application. It is used for greater than 200 kilohertz frequency application. So what are the main causes? The majority carrier. As it is a majority carrier device, the recombination of the other carriers, that is minority carrier, is very less. Recombination is less. Recombination is less. So as the recombination is very less or very small, the turn off process becomes faster. So it is around less than equal to your 100 nanosecond, and the switching loss is very small. That's why the power MOSFET is used for high frequency application. But in BJT, as it is both majority and minority carrier device, and the turn off process takes more time, so it is used for low frequency application. That should be used for less than 20 kilohertz, not more than that. And the switching loss is in BJT is very high, but compared to power MOSFET, the conduction loss is very less in power BJT. So let us see now what are the differences between BJT and power MOSFET. In BJT, it is used for high power, low frequency application. Okay, it is used for high power and low frequency application. But in power MOSFET, it is used for medium to low power, but high frequency application. The frequency range of your power BJT is less than 20 kilohertz, whereas the frequency range of power MOSFET is of greater than 200 kilohertz. You are wondering that in this frequency band, which device is used? The next device we will study is IGBT. In this frequency band, IGBT is used. See, this is medium to low power or mainly low power, and this is high power. Next is your BJT is current control device, and your power MOSFET is voltage controlled device. One thing you should remember, for same condition, the current controlled BJT requires more current than your voltage controlled power MOSFET. That means the control signal is small. Control signal is smaller than your BJT. Okay. Next, what are the again major differences? This is a majority plus minority carrier device, and this is this. Let me write it full. Majority and minority carrier device, but power MOSFET is only minority carrier device. This is bipolar. Power BJT is bipolar, but power MOSFET is unipolar. Okay. So these are the major differences of power BJT and power MOSFET. See, one thing I forgot to tell you, that his conduction loss is less, and here switching loss is less. And as the on-state resistance of the power MOSFET is high, but the switching resistance is low, that's why the power MOSFET can be used for a parallel operations also. And what is the major application of power MOSFET? The major application is your famous SMPS, switch mode power supply, and your inverters also. For high frequency application, power MOSFET is essential for inverter circuits. Okay, so I think this is all about power MOSFET and your power BJT. Remember one which is formed, the N channel which is formed, sometimes it is also known as the hotspot, the localized hotspot which is formed. I forgot to tell you. So that's all about your power MOSFET and power BJT. Let me know in the comment section below what you think about this video. If you have some queries or questions, please comment down below. Thank you for watching this video. Please like, share and subscribe. So I am planning to start power system from the next class, and also we will run the parallel course of power system and power electronics. You will get 2 videos in a single day. Okay, so let me know in the comment section below what you think. Thank you for watching.